Hey there, it's Miss Heaton, signing in to talk with you about precipitation reactions and solubility rules. This information could be found in your textbook in chapters 7.2 and 7.3. Today, I want to start by reviewing a concept we've talked about before, which is aqueous, or aqueous. We've talked about how this means that something has dissolved in water. So we saw this image with sodium and chlorine that's dissolving in water by the water surrounding each atom one at a time, turning it into an ion and pulling it out of the ionic compound. And so sodium chloride would break up into Na plus and Cl minus ions, each of which are aqueous. Now, not everything is aqueous or soluble or dissolvable in water. It's going to depend, and that's kind of what we're going to look at today. So what I want to start with is two compounds here that are aqueous that we could possibly mix together. Oops, this kind of got cut off. This says silver 1 nitrate, which is aqueous, dissolved into its ions, and sodium chromate, which has dissolved into its ions here. Now, what would happen if we mix these two aqueous solutions together? Would there be any chemical reaction? Well, let's think about this. We know that we're starting with these two compounds. When we mix them together, the clear and the yellowish solution, we see that a clear solution forms and an orange solid forms. Why does that happen? Well, what's happened is we formed a precipitate, which is a solid. It's a solid formed when you mix two aqueous solutions. This happens sometimes, not all the time. But how could we figure out what that solid is? Well, if you look at this molecular level picture, it illustrates that the CrO4 and the kind of bluish silvers are on the bottom here, kind of combined as a solid. That's your orange solid. And then the NO3 and the Na plus are still aqueous, still dissolved in solution above. So the way we would write this, thinking back to our Unit 6 displacement reactions, we would say that the silver would stay where it is, and then like the nitrate and the chromate would switch places. So it would be Ag with CrO4, although we do have to look at charges. CrO4 is -2, Ag is +1. So this would be Ag2 CrO4. There'd be 2 silvers for every 1 chromate. And that was our solid. And what's left over would be Na and NO3, which are +1 and -1. So it would just be that. And they would be aqueous. And then we'd have to balance the equation. Boop, and a 2 here. And that would be balanced. So what we're going to talk about today is, well, how do we know without being told what the solid is? How can we predict which solid should be formed? And the way we can do that is with the solubility rules. You do not have to memorize these. These will be given to you on any test or quiz. In fact, your teacher hopefully has already given you a copy of them. And these rules tell us through experimental data that has been collected over time what generally will be soluble or insoluble. Soluble, again, remember, means that it has dissolved. It's aqueous. Insoluble means it will not dissolve, so it will precipitate or fall out of solution as a solid. They generally go from things that are more soluble to things that are less soluble. And there are some exceptions, so make sure you pay attention to those when you are predicting whether a solid will form when you mix two aqueous solutions together. Your book has a nice picture that I really like, figure 7.3, that illustrates this visually. I think it's a little bit cleaner, although it's not quite as complete of a picture. So let's try an example here. Your book says there are 3 steps to predicting whether a precipitate will occur. The first is to write down the reactants as they exist before any reaction occurs. Remember that when a salt dissolves, its ions separate. And so here we have AgNO3, silver nitrate, which will be Ag +1 and NO3 -1. And BaCl2, which will be Ba2+. From where it's at on the periodic table, we know it had 2 valence electrons, so it will take on a +2 charge in a compound. And Cl1-, and there's 2 of them, and so they will separate into 2 separate ions. How will these combine to make a new compound? Well, we know from our previous experience is that the positive of one will end up with the negative of the other compound. So we know that the Ag and the Cl will go together. Ag has a +1 charge, Cl has a -1, so it'll just be AgCl. Let's leave a space here, so later we'll come back to whether it will be a solid or aqueous. We know that the Ba will end up with the NO3. So it'll be Ba, which has a +2 charge, and NO3, which has a -1 charge. Ooh, okay, don't forget to crisscross your charges so that the charges have balanced out. So we're going to need 2 of the nitrates to make the charge balance out. Now that's not what our picture shows, because our picture is only reflecting what we put in. We may have to add another one of each compound to make the charges and the atoms balance out. So we see that 1 Ag will combine with 1 Cl, and 1 Ba is going to need actually 2 NO3s. So we're going to need to add another NO3 for each barium, and we're going to need to add another another Ag to combine with our Cl. So in the end, our picture, our picture should look like this: an Ag with a Cl, an Ag with a Cl, and then a Ba with an NO3. Now, to know whether they're actually going to stay together or, again, dissolve, become aqueous, and separate in solution, we have to look at the solubility rules. So we're looking at silver chloride and barium nitrate. So let's look at our solubility rules and see what this tells us. So we had AgCl and BaNO3, 2. So looking at the nitrate, it says here that all nitrates are soluble. So soluble means that it dissolves, so this will be an aqueous compound. AgCl, here it says Cls are soluble except AgCl. Okay, so if it's not soluble, it's insoluble, so it will be our precipitate. It'll be a solid. So in our equation, we would write AgCl solid and BaNO3 to AQ. And when we balance this equation, like we kind of did on the previous page, we find that we need 2 AgCls and 2 AgNO3s. That's why I've drawn 2 AgNO3s here. And at the end, we said that there would be AgCl. Now this is solid, so that means it's not going to break up into ions. In fact, it's going to sink to the bottom as our precipitate. So this would be our precipitate at the bottom. And then dissolved in solution, we would have the nitrate, 2 of them, for every 1 barium. And those would still have the charges on them, whereas the things that are solids would not have a charge on them. Those charges have been canceled out because they're in a compound. So here's another way to represent that, where you have the AgCl together at the bottom, and then the Ba and the NO3 still have their charges as ions. You don't have to draw that picture every time, but I think it helps visualize what we're doing and why. Let's try another example. This is the example we're going to carry through the rest of our screencast here. So we're going to start with barium nitrate, Ba with 2 NO3s, and sodium carbonate, 2 NAs for every 1 CO3 2 minus. We're going to predict the products just like we've been doing. So we know that the positive of one will go with the negative of the other. Though it's not representing switching. So we'll end up with Ba that has a plus 2 combining with the CO3 2 minus. Oh, that's really nice. Those charges are going to cancel out. We'll leave a spot to tell whether it's aqueous or solid. And then the NAs will go with NO3s. And if you look at it, each Na plus will go with 1 NO3 minus. So that's going to work out pretty well. And we don't know whether that will be solid or aqueous yet. We do need to balance the equation before we proceed, and it looks like there's 2 sodiums and 2 nitrates, so we're going to end up with 2 sodium nitrates. And I think that's the only coefficient we need to balance. This is our molecular equation. Now, we do need to look at our solubility rules to figure out what state of matter we're going to have, so let's look at these. We had NaNO3 this time, and we had BaCO3. Whoop. Hang on one sec. And we said BaCO3. Okay, so looking at the nitrates, it looks like nitrates are all soluble, so this will be AQ. And the carbonate salts are soluble if they're with a group 1 metal. That means from column 1 on the periodic table, or with ammonium. And all others are insoluble. So barium is in column 2, group 2, so it will be insoluble, so it will be our solid. So going back to our equation, we said that the barium carbonate will be solid, and the sodium nitrate will be aqueous. This is our molecular equation, so this is the first step in our process. The next step is to write the complete ionic equation. This is going to show all things that are soluble ionic compounds, written as ions. So let's take our molecular and write it out as a complete ionic equation. Anything that is aqueous we will write as its charged ions. Anything that is solid we will not. So it would look like this. Whoops. It look like this. The barium nitrate would break up into one barium and two nitrates, each of which are aqueous and have charges. You have to write the charges in. The sodium carbonate would break up into two sodiums and one carbonate. That 3 does not mean that you have 3 COs. It means that you have one carbonate ion with a -2 charge. The barium carbonate is a solid, so it stays together. And then our sodium nitrate, we have 2 of those, so we'll end up with 2 sodium ions and 2 nitrate ions. I know it's a lot of work to write it all out, but this is really important because it's going to show us what is actually participating in the reaction. The things that aren't participating are called spectator ions. These are things that are just watching the reaction occur. They're not participating directly, they're just kind of there to balance out the charges. And so if we look at our complete ionic equation, look at things that are both reactants and products, but don't change. So we have Na plus and Na plus. It's exactly the same before and after the reaction, so it's spectated. Another thing that spectated were the 2 nitrates. They were the same before and after the reaction. So our spectator ions are NO3 minus and Na plus. You don't have to write 2. The net ionic equation, net means overall. So the overall net ionic equation is going to show us only the things that actually changed, or actually participated in the reaction. Since Na plus and NO3 were our spectator ions, they're not going to appear in our net ionic equation. We would just write Ba plus 2 AQ plus CO3 2 minus AQ makes BaCO3 solid. That would be our net ionic equation. Okay, that's it, folks. Let's try another example. Try this one on your own for a second here. If you click on this link, I don't think it's going to work here. Yeah, if you click on that link or type that into your web browser, you can see this reaction actually occur. It's pretty sweet. So start by writing the molecular equation, then the complete ionic, then the spectator ions, then the net ionic. So hit pause and then tune back in for the answers. Okay, let's go through this. The molecular equation is this. The sodium iodide and mercury 2 chloride will combine to make 2 sodium chlorides and 1 HgI2. Oh, you know what? I don't know if iodine was on your list of solubility rules. Whoops, that's my bad. Hopefully you noticed that sodium chloride was aqueous because all chloride salts are soluble. The iodide salt, then, by process of elimination, would have to be insoluble. That would be your solid. So when you write the complete ionic equation, you'll break up everything into its ions from your reactant side, since it was all soluble. Make sure that the 2 here becomes the coefficient, because those 2 chlorines will not stay stuck together. They will separate into 2 separate chloride ions. The sodium chloride will break up into Na plus and Cl minus, and then our solid will stay together as a solid. Then you'll notice that Na plus is a spectator and Cl minus is a spectator ion, so you write them here. And then your net ionic equation is what's ever left. And you can write this in any order. You can write the iodine or the mercury ions first. I wrote Hg2 plus 2I minus makes 1 HgI2 solid. Okay, if you feel like you need more practice on this, here's a website where you can watch another animation of how this is solved, and then try a couple practice on your own. The bit.ly site is kind of the short link, or you could type in the whole long site. Okay, come with your questions to class tomorrow, and happy precipitating. Hopefully it's not snowing too bad outside right now.